Hi, Mr. T here. In this video, I'm going to go through the achievement standard 91166. That is demonstrate understanding of chemical reactivity. This is, of course, for level 2 NCEA, and we're looking at the 2022 paper. So I'm going to go through each question, and I'm going to give my answers how I would mark them, and then hopefully that's going to be used to you. You can see the type of phrases or the types of ways that you might solve the problems that they give to you. So if this video is helpful, don't forget to look out for other videos I've made or subscribe to the channel. Hi, it's Mr. T here again. Today I'm going to go over the Chemistry 2.4 or Achievement Standard 91166 from 2022. That is demonstrate understanding chemical reactivity. So that's the reaction paper for the NCEA Level 2 Chemistry. So the first question here, if we have a look at it, we're asked about hydrogen iodide, and it says it can be produced through a reaction of hydrogen gas and iodine, and they've given us an equation, and next to the equation they give us an enthalpy change for the reaction, which is positive 53 kilojoules per mole. They want us to write the Kc expression. Now remember, when we write a Kc expression, we're taking the equation, we're making a fraction. On the top of the fraction are the products. In this case, there's only one type of product, even though there are two of them. And on the left-hand side, on the bottom of the fraction, we put the reactants. When we draw the products, because there is a 2 coefficient in front of it, that's going to be written as an exponent. And so this is how we write the Kc expression. Now this is, you get an achieved point for writing this Kc expression. Important thing to note is Kc expressions always have square brackets around them. You don't include the phases or the gas, solid or liquid here. And make sure that you don't put anything between these square brackets. Often there's a mistake that people have made is to put addition signs between there because they get confused when they transfer from the equation. Okay, so the next part we need to do is the calculation, and here it says at 490 degrees Celsius, the equilibrium mixture has a concentration of 0.105 moles per litre for both H2 and I2. They both have the same concentration and it's stated as 0.105. While the concentration of HI is 0.711. Calculate Kc. So in this case, they want us to take the whole expression, substitute in the three values into the different parts of the equation here, and solve. So we take this Kc expression, we substitute in the HI at the top, which is 0.711 moles per litre. We substitute each of these different components at the bottom with 0.105, and here we get, this is our expression. Now if we get to this expression it's correct, they're going to give us an achieved point, and we get merit if we get the answer correctly. Now the most common mistake that people make here is they do everything right, but they forget to square the top value when they put it into their calculator. So make sure that you remember to square it, or sometimes they just forget to write down the squared. Make sure you transfer everything correctly and calculate your answer, which is 45.9. There are no units for Kc, so I don't include units, but I have written it to 3 significant figures because at the front of the paper it says we need to write all answers to 3 significant figures. Okay, so the next question here, so this achieved merit, remember merit for the right answer and achieved for using the right technique. Explain what would happen to the value of Kc if the temperature of the equilibrium mixture was increased. Okay, so if they're talking about changing the temperature, we know that there will be either the forwards or the backwards reaction will be favoured, and the reaction that will be favoured is the endothermic reaction, because endothermic absorbs the heat or removes the heat from the mixture, the heat that we've added more of by increasing the temperature. So what we do is we look back at our equation on the previous page. They've got a value here of plus 53 kilojoules per mole, and we should know that this enthalpy value being positive means that the forwards reaction is endothermic. That means the backwards one is exothermic, but the forwards reaction is endothermic. And here, because we've increased the temperature of the mixture, the endothermic reaction is going to be favored. So we want to write that down for a start. We've increased the temperature, the equilibrium. Make sure you try and put this phrase in here, which is will oppose the change by favoring the endothermic reaction, and make sure you say that the endothermic reaction will absorb the extra heat. That's why that reaction has been favored. So we're actually explaining instead of just describing. So if we get that point down, get achieved. Actually, if we just identify it's going to go in the endothermic direction, we get the achieved. If we say that the forwards reaction is the endothermic reaction, then we're going to get the merit. If we recognize that the equilibrium is shifting to the right, we get an achieved. If we get a merit, if we work out that the reason that it's doing that is the direction of the endothermic. And finally, to get the excellence, it's a bit harder. We need to talk about the ratio, or we need to say when we increase the number of products, because this is a fraction, when the products gets higher or the reactants get lower, we increase the value of Kc. And this is important. You need to be actually quite articulate when explaining this point here. So look at the example I've got here. Therefore, the forward reaction will be favored and the concentration of the products will increase and the reactants decrease, increasing the ratio of products and reactants and increasing the Kc. Now we need to remember that Kc with temperature does change, and the way that the Kc changes is dependent on whether the forward reaction is endothermic or exothermic. And we need to be able to explain this, but this is going to be like an excellence question, so don't be too dismayed if it's a bit tricky at the moment. It's maybe the hardest part of the paper. Okay, let's look at the next part of the question. Hydrogen iodide is a strong acid. Okay, we know what that means. That means fully dissociates, or an arrow going directly to the right, whereas hydrofluoric acid is a weak acid. Double arrow dynamic equilibrium. So we're going to draw these two here because we've got the equation started for us. We're going to draw the correct arrows. They haven't drawn the arrows because the arrows are important. Strong acid, direct arrow. Now, because this is an acid, it donates its proton to the water. The water becomes the hydronium ion, the H3O+, and the I- is left behind. Remember, when an acid loses its hydrogen, it also loses a positive charge. It becomes one more negative. Now it says that hydrogen fluoride or hydrofluoric acid is a weak acid. So we write down that it has an equilibrium. Everything else is the same. It produces the hydronium ion as well and a fluoride ion similar to the top, but the difference is it fully dissociates the first one compared to partially dissociating in the second one. Now that's an achieved point. Now if we want another achieved point, all that we need to do is write down about either the first equation fully dissociating or the second one partially dissociating. So when HI is placed in water, it fully dissociates. Now, as well as saying that, we need to link the concentration of H3O+ to what fully dissociate means, which means that the concentration of H3O+ is going to be equal to the original concentration of the acid. It's going to be a high concentration. Because there is a high concentration of both the H3O+ and the I-, then the solution will be able to transfer charge easily because there's charged particles sitting in the water. This is the H3O+ and I-, and they will transfer charge from one electrode to the other, or we will say they will be a good conductor of electricity. But to make it a stronger answer, we'll say that they're able to transfer charge, and that makes it a good conductor. The second point, they asked us about two things. Explain about the pH and the electroconductivity. So I'm going to explain about the pH now. Because the H3O+ is high, the pH will be low. Okay, so remember that high concentration of H3O+ means it's very acidic, low pH like 1 or 2. So that's nicely fully explained. If we're able to identify that the pH depends on the concentration of H3O+, it's another achieved point. If we can link it fully dissociating to high concentration, that's our merit. Okay, if we can link high concentration of ions to good conductor, that's also our merit. And in the end, if we can do everything really well, we get an excellence. And the second paragraph is hydrogen fluoride partially dissociates, low concentration. Now remember, when this partially dissociates, when the dynamic equilibrium is set up, there's maybe 1,000 times more reactants than there is products. So we're going to expect a pH of about 3 or 4. as the concentration of H2O plus, remember you can use the square bracket around an ion, and that means, or around anything that means concentration of, it will have a smaller pH. But also because there's a low concentration of these ions, it will not conduct electricity well. Now I haven't explained down the bottom that conducting electricity is dependent on the transfer of charge, because they already wrote it higher up in the question. Now this is the end of the first question, and to get a good mark for this, to get the excellence, you needed 2 E points, 2 full E points. And to get the E7, you need to get the 2 E points, but with a small mistake. Now, a small mistake could have been you missed out part of the second paragraph here. We're looking, because there's 2 merits here and there are a couple of merits in the previous part of the question, we need 4 merits for M6 and 3 merits for M5. And of course, you get the achieved points based on how many A's points you're able to get. But look, you should be able to accumulate all those A points. And what you're really looking for is every now and then you're going to pick up this M5, M6 or E7, possibly even E8, and that's really going to start to get you up into the merits and excellence. But getting the achieved should be a given for anyone who's going to do some serious studies of chemistry. You'll get the 10 to 12 points easy, and if you keep studying it, you're definitely going to get in that merit and excellence range. Okay, let's look at the next question. All right, well, let's look at question 2. So here we've got methanol is being manufactured through a reaction with carbon monoxide, CO gas, and hydrogen gas, H2 gas. The equation for the equilibrium that is established is below. So we've got 1 carbon monoxide reacting with 2 hydrogen gas particles, and they produce 1 methanol particle. The chemical equilibrium has been established. The concentration of all species present in reaction are recorded and graphed below. So we've got 2 sections here. Now, for a start, look, this looks incredibly complicated. And it's the first time I've seen them try and depict an equilibrium reaction with this type of graph. But let's see if we can unpack it anyway. So we've got section A and section B, right? So you can see something happens at the intersection or the end of section A before and the start of section B. So let's see what it wants us to do. Explain how the graph shows the system is equilibrium through section A. So all that we're going to do is answer section A, right? So we're going to refer to the forwards and reverse rates in our answer. So section A, here we go. There it is, that point there. What does it look like? What can we see about the concentrations of each of those solutions? Methanol, hydrogen, and carbon monoxide. So in section A, the concentration of reactants and products stays constant. Cha-ching, achieve point. You're going to get that right there and then, right? And we're only focusing on that part of the graph because that's all that I want us to talk about. During this section, the forwards and the reverse reactions are at dynamic equilibrium and happening at the same rate. So the concentrations stay the same. So I am explaining in the second point, I'm explaining in the first point what it is. Sorry, describing in the first point and explaining in the second point. And for the first point, we're going to get achieved. And the second point, if we can say that the reverse and the forwards reaction are happening at the same rate, then we are going to get our way towards getting the merit point here. Okay, let's look at the next part. At the beginning of section B, so that's this point on the graph. Okay, let me show it. Here it is. This is the green part. On the previous page, carbon monoxide is added in the reaction vessel. Explain using equilibrium principles how the system responds to restore equilibrium. Refer to the graph. Okay, at the beginning of section B, we can see that the carbon monoxide has a sharp increase in its concentration, and that's not a natural thing. Someone's just gone and put some carbon monoxide into this vessel that contains this reaction. So it is initially increased. So I've said carbon dioxide is added to the solution, it initially increases in concentration. Writing solution here isn't really correct. I guess you could say mixture would be a better word to use here. But what did the equilibrium do once we did that? So the equilibrium opposes this change, because that's what systems at dynamic equilibrium do. And it does that by reducing the concentration of the CO2 because we added more of it. And it's going to favour the forwards reaction. If we can identify that forwards reaction is favoured, that's an achieved point. Okay. Now let's go to the next bit. In the blue bit, what has happened? Well, in the blue bit, we can see that all of the concentrations are constant again, and that's because in section B it's re-established the dynamic equilibrium again. So the Ford's reaction produces more of the product until the dynamic equilibrium is established again. So if you can identify that it's been re-established, you get an achieve point. If you can link the Ford's reaction to the decrease in the reactants, and that's what I did in the second part here, is that reducing the concentration in favor of the Ford's reaction. What have we said? Increase in products. Yep, so we've said that. Excellence. If I've included all 3 points, so I guess, look, the merit point is here. We've said the Ford's reaction goes forwards, therefore the concentration is reducing the concentration of CO2 and favouring the Ford reaction. The Ford's reaction produces more products. I've said that sort of in 2 ways. The merit is, did I include all of these components? Sorry, not the merit, the excellence. And I did. So we've got an achieved merit excellence for this point. And this is the start of question 2. Let's go on to the next part. Now, in the paper, this equation is on the previous page. You need to look back. It's actually 2 pages over. So take care when you're answering your paper to look back to the start of the question if you need to define the equation you're going to be talking about. So using equilibrium principles, explain why carrying out the reaction at high pressure is advantageous, or why it's good to the manufacture of methanol. Okay, so we want more methanol. So if I'm producing it, if this is my business, if this is my factory is to make more methanol, I want more made. So I want the reaction that's going to make more. How is high pressure going to make more? Well, we're going to remember we increase the pressure, we're going to make more of the side that has the least gas particles, or the reaction that produces the least gas particles is going to be favoured. So if the pressure is increased at a system at dynamic equilibrium, it will oppose this change. Now try and always write in this wording, oppose this change. Sometimes, depending on the marking schedule, they want you to put more detail to say that's what an equilibrium always does, it opposes change. And it favours the Ford's reaction that produces less gas particles. So I've said it a wee bit different here. I've said it favours the reaction that produces less gas particles. I've said specifically to get the excellence here, or the merit point, sorry, here. Oh no, it's the excellence. You need to say specifically how many gas particles. So there is 1 mole of gas particles on the right, and there are 3 moles of gas particles on the left. Therefore, the Ford's reaction is favoured, and that will produce more methanol. So achieved. Recognise increase in pressure favours the side with fewer gas particles. Merit links the pressure to the shift in equilibrium. You then say the Ford's reaction is favoured. Excellence, we're going to include that detail. We're going to say that there is 1 mole of gas particles on the right and there are 3 on the left. Okay, the next question. The formation of methanol from carbon monoxide to hydrogen is a slow reaction. Not good if you want to produce it, because it's going to take a long time. To increase the rate of reaction, a small amount of zinc oxide can be added. This zinc oxide can be recovered after the reaction. Okay, 2 big clues here. Zinc oxide is recovered after the reaction isn't used up, and it makes the reaction go faster. Cha-ching, catalyst, right? That's what it's going to be. Here it is. And then they wanted us to draw it on this diagram, which means we're just going to draw an alternative lower pathway, as I've drawn here. I've labelled it with the catalyst. So if we include those 2 points, we get ourselves another achieved points. We now have to explain how zinc oxide increases the rate of reaction. Refer to collision theory. So, collision theory, specifically, we're going to be looking at the amount of activation energy that's needed to make successful collisions. That's going to be the basis of our argument. So here, zinc oxide is the catalyst and provides an alternative pathway, key phrase, for a reaction with less activation energy. That's what we've got here with the smaller hump. And because the alternative pathway, more particles will have enough energy. Okay, so more particles will have that small amount of energy needed to have a successful collision. And then the final bit is there will be more successful collisions per second, or there will be a higher frequency of successful collisions. Therefore, it's going to react faster. And we're going to be going achieve merit excellence for these 3 points. That's the end of question 2. Question 2 marked a wee bit easier maybe than question 1. Well, it's not easy, it just needed less merits. So here you needed 3 merits instead you needed 4 in the other one, and 2 merits for M5, 3 merits for M6, 2 for M5. Again, if you make a small mistake at the end here, you might not have put something down like it will make it happen a far higher reaction rate, or you might have left out something about successful collision and you only got a merit in this point, but it was only a small part, then you still might get the E7. Okay, let's have a look at the last question. So we've done equilibrium, we've done some reaction rates. We're going to expect now that we're going to answer some questions or some calculations on acid bases. So this is a quite straightforward question, and as in the first one, it's saying we have a pH of 2.4. Can you calculate the hydronium ion or the H3O plus ion concentration in hydrochloric acid? So we know, we go and find from our resource sheet that this is the equation we need. H3O plus equals 10 to the negative pH, or on your calculator it's just the shift log button, then we press minus and then we put 2.4 and we get this answer, 0.00398 moles per litre. Put the unit in, it's just really good habit to get into. Now if this was in standard form, if your calculator was in standard form, it would be 3.98 times 10 to the negative 3 moles per litre. So the second part, part 2, there's one more step involved. We're going back the other way, but because it's a base, lithium hydroxide, what's going to happen is we're going to find the concentration of hydronium ions first, and then we can find the pH. And the way that we do that is we put the concentration of the hydroxide ions on the top and we divide it by 1 times 10 to the negative 14. And remember, that's the same way we would find the concentration of hydroxide ions. We would divide H3O plus by 1 times 10 to the negative 14. We substitute in the values, there we go, and we get the answer of 4.5 times 10 to the negative 14 moles per litre. We then put that into our next equation, which is the pH equals the negative log of H3O plus. That is, you just go plus minus, press the log button, and then press this concentration in your calculator, and the answer you get is 13.3, the pH. So the first one up here, because it's one step, it's an achieved calculation. The second one, 2 steps. If you got the first bit right but didn't get the second bit right, you get an achieved. If you got the second bit right but not the first one, you get achieved. If you get both, you get a merit. Okay, so the next part is 3 solutions of equal concentrations. Now this is important. They'll always say that these unknown concentrations are equal because we need to talk about how they are different, and we need to keep that bit the same. So we've got sodium hydroxide, which, look at it, sodium hydroxide, this is going to be a base. It's just going to break apart into the sodium and the hydroxide. Sodium chloride, should know or should be starting to remember that sodium chloride, table salt, is neutral, and sodium carbonate. Okay, so if we use deductive reasoning, the sodium hydroxide here we know is a strong base because it's got hydroxide right there and it's going to split apart into it. So we're going to put that one in here. We know NaOH is neutral, so we're going to put that one in. And then the last one left behind is sodium carbonate, and it must be the 11.6. It must be the weak base. How do we explain that? Okay, so how we're going to explain that is in the following way. If we put these all down right, we get achieved. Sodium hydroxide, we place it in water, fully dissociates. Okay, so this is a similar question than we had earlier. So the concentration of OH minus is equal to the concentration of sodium hydroxide. Okay, so we get a really high concentration of OH minus ions. Here we go. Because we have a high concentration of OH minus ions, this is going to be the strong base. Okay, it's going to have a highest pH. Now, sodium carbonate dissociates in water to produce sodium and carbonate ions. So here's the first part here. It just breaks apart. Now, what's happened here is this is a salt of a weak base. Now what that means, it's actually a weak base hiding. It's hiding in this salt, in this neutral compound. When we put it in water, it breaks apart, and this is a weak base. So we have to write our second equation, and that is it of CO3 2 minus partially dissociating in water. And it produces a concentration of OH ions, which is less than the same concentration that NaOH would produce. So it has a lower pH, right? Not high in the 13s or 14s, but it's down in the 11s and 12s. We remember because this is acting as a base, it accepts one proton, it becomes this hydrogen carbonate or this bicarbonate ion, produces hydroxide ions, and it has this double arrow because it's partially dissociating. Sodium chloride fully dissociates in water, produces sodium chloride ions. Look, these are neutral. Sodium chloride is neutral. That's why it has a pH of 7. Now, if you recognized that the pH or the higher concentration of BH leads to a higher concentration OH minus leads to higher pH. That's an achieve point. If you had two of these, I haven't put the fourth equation, two of these four equations down, you get achieved. If you explained the difference in pH between these, the sodium carbonate and sodium hydroxide is to do with the degree of dissociation, okay, then for two substances, then you would have, or for these two substances here, you get a merit. And basically, if you put everything down, you're going to get the excellence. Okay, so this is the last part of the paper, the last part of question 3. They're referring to the weak base and its reaction with the strong acid here. We've got basically sodium carbonate reacting with hydrochloric acids turning into sodium chloride plus water plus carbon dioxide. Now what they're doing here in the graph is they're measuring the amount of carbon dioxide produced per second and they're plotting it. So plotting the amount of carbon dioxide produced, and they'll collect that maybe in an inverted measuring cylinder, and they'll measure how much per second is produced. Now the reaction was carried out both at 25 degrees and 50 degrees. Okay, so that should trigger us right at the start and tell us they're going to ask about temperature change here, because we've got two different temperatures. And the amount of carbon dioxide was plotted on the graph below. In the reactions, the same concentration and volume of each solution was used. We would expect that if they're changing just one thing at a time. Explain the effect on increasing the temperature on the rate of reaction. In your answer, you should refer to collision theory. Well, we expected that. They're always going to ask us about temperature and collision theory. Consider both the rate of carbon dioxide production and the total volume of carbon dioxide formed for each reaction. Refer to the lines on the graph above. Okay, so total volume is really interesting how they said that as well. At the end, we're supposed to say that the total volume is the same because the amount of reactants is the same. That's just a line we're going to put right at the end, okay? So let's go on and see if we can answer this. The first thing we're going to say is, at 50 degrees Celsius, the curve has a steeper gradient. So look, the blue line is steeper, means it's reacting faster and producing carbon dioxide more quickly. Excellent, that's our first point. Second point is we're going to say, well, 50 degrees, the HCl particle is going to have more kinetic energy. Okay, that's important as well. The next point is our first collision theory statement. We're going to make two independent statements. Because the particles, because of this, because they have more kinetic energy, I could write kinetic energy again in the third point, but I said it in the previous, I don't need to. Because of this, the particles are moving faster and we'll have more frequent collisions. Okay, that's the first point. Make sure you talk about the frequency of collisions or collisions per second, because it's moving faster. And the next point is, because the collisions have more kinetic energy, they're gonna more of the collisions will have the kinetic energy required to overcome the activation energy. So there will be more successful collisions. Okay, that's the second independent point. So those third and fourth point here are the two collision theory points we have to state down. I'm going to summarize this. There will be a higher frequency of successful collisions and there will be a higher reaction rate. Just to make sure I've covered everything, the total volume will be the same because the total amount of reactants is constant. That's my last point. Okay, so, and then we have, I haven't written down that last point, but you should write it down. So if we recognize the kinetic energy is increased, we get an achieved. If we state the same volume of carbon dioxide is produced, we get the achieved. So that last point gets me that extra achieved point. If I link the frequency of the collisions to the steepness of the line, or increased kinetic energy of the particles, or increased collision exceeding activation energy, so any of these points from the first, the third, or the fourth, then I go and get my merit. Excellence. I need to fully explain everything with the graph. So I need to make sure, I'll just write the last one in here. I might not come up at the right time. And remember, that is that the same amount of carbon dioxide is produced because they both have the same amount of reactants at the start. That's the end of the paper. That's the end of question 3. For question 3, 2 E points, you get an E8. 2 E's with a small mistake, you get E7, and then you get 3 M's for M6 and 2 for M5, and we add all of this up, and we're going to expect we get like an 8 or no 7 maybe for this one for passing of A's in total, or points in total, and we get 14 for the merit, 14 or above, and then 19 or above for excellence. Hopefully this has been helpful. If you found this helpful, look out for the other chemistry videos I've got here that go over the old papers, and make sure you use them in preparation for your exams. And good luck with your exams. Don't forget to like, share and subscribe if you find these videos helpful. Leave any comments if you have any questions or if you notice any mistakes. Thanks again. I hope you enjoyed the video. Well, I hope that it's useful anyway. I hope that video has been useful. If you have any questions, don't forget to put that down in the comment. I'll see if I can answer them for you. Don't forget to subscribe if you want to see some other videos that I have made about this, and give it a like if you found it helpful.